Hello, and thanks for joining us. Today's topic, understanding the fan laws. The fan laws outline the relationship between variables in HVAC fan performance. A change in performance of one variable can be calculated by using the changes of another. The variables typically covered in fan law are as follows: fan speed, rotation per minute; airflow, cubic feet per minute; static pressure, measured in inches of water column; and power, measured in brake horsepower. Let's break down fan law 1. The first fan law calculates the relationship between a fan's speed and the airflow it moves. This is a straight calculation, meaning there is no exponent or root function involved. Fan law 1 states that CFM2 is equal to RPM2 divided by RPM1 times CFM1. If we reverse the known values, RPM2 equals CFM2 divided by CFM1 times RPM1. Note that the CFM and RPM are interchangeable. This is true across all the fan laws. Moving on to fan law 2. The second fan law calculates the relationship between a fan's speed or airflow and the pressure the fan produces. Unlike the first fan law, however, one form of the equation will use the exponent 2, while the other will utilize the square root function. Fan law 2 states CFM2 equals the square root of static pressure 2 divided by static pressure 1 multiplied by CFM1. If we reverse the known values, static pressure 2 equals CFM2 divided by CFM1 squared multiplied by static pressure 1. Note that again, CFM and RPM are interchangeable. On to fan law 3. The third fan law calculates the relationship between a fan's speed or airflow and the power required to produce it. We will now use the exponent 3 for one form of the equation and the cube root function for the other. Note that amps can be substituted for brake horsepower in fan law 3. Fan law 3 states CFM2 equals the cube root of brake horsepower 2 divided by brake horsepower 1 multiplied by CFM1. If we reverse the known values, brake horsepower 2 equals CFM2 divided by CFM1 cubed multiplied by brake horsepower 1. Yet again, CFM and RPM are interchangeable. Let's practice. Imagine that we have a fan that was designed to deliver 2300 CFM at 1565 fan RPM, 1.0 inches static pressure, with the motor operating at 2.0 brake horsepower and 5.9 amps. When we measure the fan, we find that it is delivering 1967 CFM at 1221 fan RPM, 0.59 inches static pressure, with the motor operating at 1.03 brake horsepower and 3.0 amps. If we adjust the drive assembly to achieve the design airflow of 2300 CFM, what would the new operating conditions be? The new RPM would be 1,428. The new static pressure would be 0.81 inches. The new brake horsepower would be 1.65, and the new amp draw would be 4.8. So let's take a look at how we got these new numbers. First, we'll look at RPM. We used fan law 1 to calculate the new RPM. We took 2300, which was the new CFM, divided by the original CFM of 1967. We times that number by 1,221 RPM, which gives us 1,428 RPM. Next, we looked at static pressure. For static pressure, we had to use fan law 2. Again, we took 2300 CFM divided by 1,967 CFM, and then we squared it. We took that number and multiply it by the original static pressure of 0.59, which gives us 0.81 static pressure. Brake horsepower in amps utilizes fan law 3. Fan law 3, we use 2300 divided by 1967 cubed. We multiply that by brake horsepower of 1.03, which would give us 1.65, or by the amps of 3.0, which would give us a new amp draw of 4.8. Okay, one last thing. The final equation or principle we should cover is the effect changes in air density will have on fan operation. This is sometimes referred to as fan law 4, and it breaks down like this. Changes in air density will impact static pressure and power performance of a fan system. However, the volumetric flow rate, CFM, does not change based on air density. If we solve for brake horsepower 2 equals density 2 divided by density 1 times brake horsepower 1. If we solve for static pressure 2 equals density 2 divided by density 1 times static pressure 1. Again, the CFM will not be affected based on changes in air density. The flow will stay the same, however the power and pressure required to move the air will not. Thanks for watching, and I hope this video was helpful. Look for more videos covering TAB and commissioning topics, and follow us on LinkedIn, Facebook, and YouTube.